In this video, I'm going to tell you a story. This is a story about numbers, specifically very large whole numbers, and how important it can be sometimes to do the math in advance to make sure that what you are planning to do is actually doable. And along the way, using only basic math, we might find ourselves sharing a little wonder for those numbers. Now, let me say right off, I'm not a mathematician. But this is a true story that happened to me several years ago when I was working for a company that published educational assessments. In other words, tests. One of those tests was a tool students and young adults would use to explore the kinds of career paths they might want to consider. The test was originally published as a paper test using our old friend, the number 2 pencil. The test asked the students 120 questions about what they liked to do and what they felt they were good at. And for each question, the students would provide one of 5 possible answers from A through E. Then software would crunch a bunch of numbers and produce a report that would indicate some career possibilities the student might want to think about as they move forward in their schooling. Eventually, the company produced a computerized version of the test using state-of-the-art hardware like this. The test was provided on advanced storage media like this that the students could use on their computers at school. They would just load the diskette, answer 120 multiple-choice questions, and review the report that helped to identify some possible career choices. Shortly after I joined the company, they decided it was time to rewrite the software so the test could be administered over the internet and the students could take the test from home. The idea was that this would provide a more thoughtful environment away from school where students could take time to consider their answers and think hard about the career suggestions that the scoring process would provide. That scoring process was somewhat complex, and we wanted to be absolutely sure that the new internet-based version produced the same results as the old version. So we came up with this idea. Why don't we just create a database of all the possible answers for the 120 questions in the test? Then, to test the scoring, we would feed all those possible answers to both the old and the new software, and we would be absolutely certain we had checked every possible combination of answers. We envisioned our database looking something like this spreadsheet, with 120 columns representing the 120 questions. The first row of the database shows a sample where all the question responses use the letter A. But if we zoom in, scroll right, and then scroll down, we can see how we can systematically cycle through all of the possible responses until finally getting to the last row where every question response has the letter E. So, the question that immediately comes to mind is this: how many different possible answers are there? In other words, how many rows of different answer responses do we need in our database? Well, luckily, this is an easy question to answer. All we need to do is take the number of possible question responses, remember that was 5 possible from A through E, multiply that by 5, giving us 25, and continue to multiply the answers by 5 until we've done that 119 times, one multiplication for every question after the first one. So that's 5 to the 120th power. And here is the number that results when we do the math. Due to software limitations, this is an approximation, but it's close enough for our purposes. This is the number of total possible answer combinations. And as you can see, this is a very large number. So, needless to say, we abandoned the notion of creating a comprehensive database of all the possible question responses. But we did have a little fun devising ways to help us comprehend the enormity of this mind-boggling number. The trouble is, using our standard notation, our brains have difficulty with the long sequence of digits, commas, and zeros. We thought it might help our understanding if we could compare this number to another very large number. So we came up with this. How about the number of seconds since the beginning of time? Now that number has got to be a whopper. Scientists tell us that roughly 13.8 billion years ago, something amazing happened, the Big Bang. From a tiny, infinitesimally small point, the entire universe came into being. If we were to calculate the seconds since that incredibly ancient event, we would rightfully expect that to be a very large number. So let's do the math. We'll start with 13.8 billion years. There are 365.25 days in a year. Multiplying those two numbers will give us the total number of days since the Big Bang. And there are 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So doing the multiplication of those numbers shows us the approximate number of seconds since the universe was created. And this is a little surprising. As you can see, this number is much smaller than the number of rows in our hypothetical database. But just looking at these two numbers, it's still difficult to understand how they compare. Let's see if we can create a graph to show the relative sizes of these two large numbers. That should give us a nice visualization. In this graph, we'll have one bar that represents the number of seconds since the Big Bang, and a second bar that represents the number of rows in our hypothetical database. Remember, all we are doing is comparing the size of the first number to the size of the second one, so even though these numbers represent different things, it's still a valid comparison. Now let's say we make the first bar 1 inch high. Using the same scale, how high does the second bar need to be? Well, that's easy. All we need to do is divide the larger number by the smaller one, and that will tell us how high the second bar needs to be in inches. And here it is. But how big is that really? Now here's something fun you can try. Ask a friend how tall they think that many inches might be. Let's look at some of the answers you might receive. We'll start with the Empire State Building. For many years, the Empire State Building was the tallest building in the world at 1,454 feet. But that only comes to 17,448 inches, so obviously we have to try something much bigger. How about the diameter of the Earth? The Earth is roughly 8,000 miles in diameter. That comes to 42,240,000 feet, or 506,880,000 inches. Well, that's a lot of inches, but we are still a long ways off. Let's try the distance from the Earth to the Sun. The Sun averages about 93 million miles away. So doing the math, that comes to about 491 billion feet, or roughly 5,892 billion inches. Even if the second bar of our graph went as far as the Sun, it would still be far short of the required number of inches. We need to go much bigger. Here is an artist's rendition of our Milky Way galaxy. Our Sun is one of an estimated 100 to 400 billion stars within the Milky Way, which has an estimated visible diameter of 100,000 to 200,000 light years. Using that upper limit and converting the light years to miles and then to feet and then to inches, we eventually come to this. And as you can see, even the length of the Milky Way galaxy is not big enough to contain the height of the second bar in our graph. So let's cut to the chase. No one knows how big the universe is. Scientists have come up with the idea of the theoretical limit to the observable universe. Current thinking calculates the diameter of the observable universe to be 93 billion light years. Now let's imagine we can jump into a wormhole, travel to the edge of our observable universe, and look back where we came from. In this image, each tiny pixel of light might represent a supercluster of galaxies. Converting those light years to miles, then to feet, and to inches gives us this number, which is still far smaller than the required number of inches for the second bar in our graph. In fact, by doing one last division, we can calculate that the second bar in our graph would require this many observable universes stretched end to end. And remember, in this exercise, we were just trying to get a better understanding of the enormity of our hypothetical database by comparing the number of required rows against the number of seconds since the Big Bang. Eventually, we finished the internet-based test, and we also learned some valuable lessons along the way. The main one being that when working on problems of scale, it can be a big mistake to make assumptions about what is or isn't possible. For instance, when testing software, it is almost never possible to test every single combination of inputs to make sure that the software behaves as intended. Instead, software quality assurance professionals develop their test cases strategically to provide confidence that their products are working correctly. Also, this exercise was a clear reminder that our conventional method of representing numbers is incredibly powerful. With just a few digits and commas, we can represent numbers ranging from the everyday, like the number of pens in my pen cup, to the uniquely uncommon, like the size of the universe, and even beyond. And finally, we learned that our brains are capable of grasping, comparing, and understanding numbers of all sizes, even numbers greater than any number of things we might encounter in our entire universe. This ability is a magnificent accomplishment of the human mind, and it tells us that, in a sense, the space inside our heads is even bigger than the space outside. So the next time you are faced with a problem of scale, whether you are building a house, designing a product, planning a trip through space, or making and testing software, don't forget to, well, you know what to do.